Okay, so in this lecture, what we will talk about is that we will talk about instruction scheduling, which is the which is another phase in the compiler, right? That we talked about. In this talk, we will specifically do some initial introduction for why instruction scheduling. Then let's talk about basic block instruction scheduling. And then after that, we will talk about global instruction scheduling. And in global instruction scheduling, we will typically talk about trace block scheduling as well as super block scheduling. Then, if time permits, we will very briefly talk about instruction scheduling for loops, which is what is called software pipelining, which is one of my favorite topics. So let's try to see if we can squeeze some parts of software pipelining also in our discussion, right? So instruction scheduling is important because modern processors can overlap execution of independent instructions. So you can in fact fetch and decode multiple independent instructions together and execute them in multiple function units. Therefore, instruction scheduling can essentially help these processors by exposing the instruction level parallelism which is available in the program, right? Because as somebody was pointing out, the compiler has this full picture, therefore it can see and then it can expose the parallelism that is available in the program so that the hardware can exploit it. This is for superscalar processors which can do a lot of runtime reordering of instructions, but it is also it is even more useful for machines like VLIW machines or EPIC, which where the compiler has to play the real heavy lifting in terms of the compiler has to expose these parallelism and then pack these independent instructions in terms of long word instructions, right? So this is where instruction scheduling is useful. Instruction scheduling is also useful, as we talked about in the very first lecture, that when you have pipeline hazards due to data hazards or control hazards, instruction scheduling can reorder instructions, move instructions into the delay slots, or move instructions in between dependent operations so that those stalls can be hidden. So this is the example that we saw the other day. It's the same example here. In this particular example, we are assuming that if there is a stall between the load and the immediate dependent instruction, right? For example, like what you see here between the first load and the add instruction, because load produces a value in R3, which is being consumed by the subsequent instruction. Similarly, here load produces a value in R13, which is being consumed in a different subsequent instructions. If you want to execute this sequence of instructions, then because of these dependencies, there will be one stall that will be incurred between the load and add instruction here, and another stall that would be incurred between the last pair of load and add instructions. However, if you try to, right, these are the dependencies that we talked about, which causes the stalls. But now if you try to reorder these instructions in the following way, right, you can actually move the load instruction from here to, a place above. And because this load instruction is not dependent on any of these two instructions, you can move it ahead of that and you can put it in the slot between the load and add. And therefore, this stall cycle between this R3 and this R3, the use of R3 can be avoided. And because you have moved the other load instructions also ahead, the dependence between this R13 and this R13 is easily satisfied and you don't have to incur any stall. So instruction scheduling is all about moving instructions, but at the same time, you have to make sure that the dependencies between instructions are always maintained. Particularly this true dependence that you talk about between this R13 and this R13 is maintained. Similarly, this dependence between R3 and R3 is maintained. If you have other forms of dependencies like output dependence or anti-dependence, they also should not be violated. But some reordering is possible if you try to do some register renaming. Remember that anti and output dependencies are false dependencies, and they happen only because you are reusing the same register variable name, or you are reusing the same register name, right? Therefore, if you do register renaming and use some other register, then you can remove the anti-dependency or output dependency with regard to the other register. But of course, you have to still make sure that that doesn't introduce newer anti or output dependency. So as long as you can remove these dependencies by doing register renaming, and then if you want to reorder your instruction, it's perfectly fine, right? In some cases, we will also do some offset adjustments to take care of some of these anti-dependencies and so on. I will give you an example of this when we talk about a specific example for VLIW schedule, right? But in general, when you do instruction scheduling, you have to obey all dependencies, true dependencies as well as false dependencies, anti and output dependencies. But anti and output dependencies can be eliminated by register renaming. And once you eliminate those anti and output dependencies, then of course you are free to move your instructions around, only making sure that all the true dependencies are satisfied. Okay, so that's the basic idea in instruction scheduling. And as I mentioned earlier, instruction scheduling helps to reduce pipeline stalls. Instruction scheduling helps to expose instruction level parallelism because independent instructions can be marked. And instruction scheduling reorders instructions and puts independent instructions together so that instruction level parallelism can be exploited. Right, so these are the benefits of instruction scheduling. Now let's once again look at this VLIW processor and then see how instruction scheduling can be beneficial here. In VLIW processors, these independent instructions have to be packed together, right, and presented to it so that it can exploit instruction level parallelism. Let's see an example for this, and let's see what instruction scheduling can do for this. I will assume this simple C code where you are trying to modify each array element by adding a scalar value to it, right? Now, the assembly code for this would look something like this. There is a load instruction which loads this value from the array location. Then you do an add operation. And then after that, you store the value back into the array location, right? And the three instructions, the integer instructions below, are essentially incrementing the array pointer and decrementing the loop count, and then branching if the loop count, the number of iterations is not over, right? Now, let's say that we try to schedule code for a VLIW architecture having 4 different functional units: 1 integer functional unit, 1 floating point function unit, 1 load store unit, and 1 branch unit. We will also assume that the load instruction takes 2 cycles to complete, and the floating point instructions take 3 cycles to complete. That means that between a load and a dependent instruction, right, there has to be at least 1 instruction in between if you don't want to incur any stall. And similarly, between a floating point instruction and another instruction which is dependent on the floating point instruction, there has to be 2 cycles or 2 instructions in between if you don't want to have any stalls. Otherwise, you have to incur up to 2 stalls for that, right? So these are the conditions that are given by the target architecture. And then these are the conditions which are given to the instruction scheduler. And let's say this code is what is given to the instruction scheduler with these conditions, right? Obviously, in this particular case, we have very few instructions to schedule. And as you can see that there is a lot of dependency. This load instruction produces a value F0, which is being consumed by the floating point add instruction. That produces a value F4, which is being consumed by the store instruction. Therefore, there is no parallelism at all between these instructions. And of course, this add instruction increments the pointer, which is what is being used by the load which is what is being used by the load instruction and the store instruction. The subtract instruction decrements the count, which is what is being used by the branch instruction. So if you take this loop itself and then try to schedule it for a VLIW processor, you are going to not exploit any instruction level parallelism, maybe very little instruction level parallelism, and you are also going to incur a lot of stalls because of the dependencies. So what we will do is that we will unroll the loop a number of times. Unrolling the loop essentially means that within each iteration, you are going to perform for different values of I. Instead of this loop, right, iterating n times, each iteration doing for 1 element, we will, let us say, iterate the loop n by 4 times, and each iteration doing for 4 elements, A1, A2, A3, A4, something like that, right? So when I do that, essentially what happens is that the useful part of the code, which is this part, right, is actually replicated 4 times. The control transfer part, which is basically incrementing the pointers or decrementing the loop count, etc., they are executed only once, right? So that is essentially what happens when you do loop unrolling. So let's assume that this loop is unrolled maybe 5 times, and then it is scheduled for the VLIW processor with these kind of conditions. I'll show you what is the resulting code, right? You can see the resulting code over here, where the memory operations are put in one column, the floating point operations are put in another column, and so on. And each one is one VLIW instruction. In some VLIW instruction, there is possibly only one operation. In some other VLIW instruction, there is up to 3 operations together, right? But what you can see here is that corresponding to the 5 times unrolling, you see that there are 5 load operations. And each time you try to load from a different location, like 0, 8, 16, and so on, these are the offsets, which essentially corresponds to A0, A1, A2, A3, A4, right? And then at the end of it, the array pointer is incremented by 40, which corresponds to 5 elements. So you go to A5, then A6, A7, A8 are being fetched from there, and so on, right? So you essentially have multiple load operations corresponding to the number of times that you have unrolled, and multiple add operations and multiple store operations that you talk about. Now you can see that the dependence from this F0 to this add instruction is separated by one instruction in between, and therefore this does not incur any stall. Similarly for each one of those load instructions, correct? And similarly, from this add instruction which produces the F4 value, the store instruction which consumes that F4 value is separated by 2 instructions or 2 cycles, and therefore it is no stall and it can actually go ahead and execute it, right? So what I have done is that I have essentially unrolled the loop a number of times, and I have tried to schedule this as much as possible. And this is the best possible schedule I can get for this particular loop on this architecture. And now you can see that my 5 iterations are being executed in 10 cycles. That means on an average, I am able to execute each iteration in 2 cycles. This is the best possible speed up that this instruction schedule can give on this VLIW architecture, right? There are a few small things that I will quickly point out. I talked about anti-dependency and output dependency. You can see that the subtract instruction modifies, sorry, not the subtract, the add instruction modifies the R1 register, but on which the store instruction is dependent. But because R1 has been modified by 40, I'm actually using some offsets which are negative, which is adjusting for appropriate values. When you get time, you can go ahead and find out that when R1 is incremented by 40, right, this offset which should have been plus 24 now becomes minus 16. This offset which should have been 32 now becomes minus 8, right? So this corresponds to A4, A9, and so on. So that will be with an offset of minus 8, whereas this corresponds to A3, A8, and so on, which will be with an offset of minus 16 when R1 is incremented by this one. And there is a small mistake here. This should have been 5, not 1. Okay, this should have been 5, because you are doing 5 iterations together. Okay, so this is what an instruction scheduler is supposed to do, right, for a VLIW machine. The question is, how do we write this kind of an instruction scheduler in your compiler? What all needs to be taken care of? How does it make sure that these stalls are taken care of? How does it make sure that the dependencies are not violated, yet the operations are scheduled in such a way that you get the maximum throughput or the maximum throughput for the iteration, right? That is the question that we want to address in instruction scheduling, right? This is, of course, for the code which is there inside the loop body, which is fortunately happens to be a single basic block, right? But there are also various other situations which we'll talk about, where we talk about global instruction scheduling or software pipelining and so on. Of course, VLIW architectures were introduced way back in the 80s, but in modern times, you have this, in 2000, there was this explicitly parallel instruction computing, or the Itanium processors, which also had VLIW. DSP processors, and as Professor Ramakrishna pointed out, Qualcomm processors have VLIW in them. The ATI Radeon GPU has VLIW. It has a 5-way VLIW in these architectures. So for all of these architectures, instruction scheduling is an important aspect, and it has to do this. As I mentioned earlier, instruction scheduling is to reduce pipeline stalls and also to expose parallelism so that these VLIW architectures and superscalar architectures can exploit them. So whenever you do instruction reordering, the instruction reordering must make sure that the data dependencies are satisfied. All dependencies are satisfied, correct? And when you do instruction scheduling for things like VLIW architecture, you also have to make sure that the packed instruction has exactly that many number of load instructions, that many number of floating point instructions, etc., as the number of functional units that you have in your architecture. That aspect is essentially what is mentioned as the resource constraint. We saw in our VLIW schedule exactly one load instruction, one load or store instruction, one floating point add instruction, and then maybe one integer and one multiply instruction in every cycle, right? Because that essentially is to meet the resource constraint of the architecture. When you talk about instruction scheduling, you can talk about instruction scheduling within a basic block, or you can talk about instruction scheduling across basic blocks, which is basically what is called the global instruction scheduling. And when you do global instruction scheduling, you also have to worry about the control dependence, right? And whether when you move code across basic block, what happens if the control doesn't go that way, right? That's something that you need to take into account. We will talk about that as well in instruction scheduling. So let's very quickly talk about basic block instruction scheduling, right? So it's essentially instruction reordering within a basic block, right? And we want to do this to minimize the number of stalls or to maximize the parallelism which is exposed, but we have to still make sure that the dependence constraints are satisfied and the resource constraints are satisfied. Again, this problem of reordering instructions, right, is an NP-complete problem. And to solve this for resources greater than or equal to 2 is NP-complete. And again, that could take exponential amount of time. Therefore, you resort to heuristic methods, which can give you efficient schedules. And these heuristic schedules can again be either operation-based or cycle-based. I'll give you examples of these things as we go by. Right? You can also formulate this optimal instruction scheduling problem as an integer linear programming problem. And of course, when you formulate this as an integer linear programming problem, it's an NP-complete problem, and it might take exponential time. You can also come up with various kinds of heuristics or evolutionary kind of solution methods like genetic algorithms and so on, and can come up with a near optimal, right, heuristic instruction schedule for them. Okay, so before we go into the details of this, first thing that we want to talk about is that given a sequence of instructions, how do you represent all the dependencies in them? Typically, we represent this using what is called a data dependence graph, in which the nodes represent the instructions and the edges between nodes represent data flow. So we can say that if one instruction produces a value which is being consumed by another instruction, then there is an edge from the producer instruction to the consumer instruction, an edge from U to V if there exists a true dependence from U to V and so on. So here is an example sequence of instruction, and you can see here that the add instruction produces a value into R1, which is being consumed by I2 as well as I3. Therefore, there is an edge between them, right? And of course, I2 and I3 produce values in R3 and R4, which are consumed by I5, and therefore, you see these edges over here, right? And in this dependence graph, we can also add the amount of time that each instruction would take to complete. For example, we said a floating point add instruction might take 3 cycles to complete. The load instruction might take 2 cycles to complete. An integer add instruction might take 1 cycle to complete, right? That information is embedded as a weight for each of the nodes. People either add this to the weight of the node or add it to the weight as the weight of the edge. Whichever way you do, it essentially tells you that it takes that much time, right, for the node to complete its execution. Right. So what is a legal schedule? A legal schedule is one in which a node is allowed to execute only after its predecessor nodes have produced the value. For example, here if you look at it, the node I4 can execute only after I2 and I3 have produced the value, right? So this is the true dependence that we are talking about, right? Because I4 is dependent on both I2 and I3. So unless I2 and I3 have completed their execution and produced the value, I4 cannot start its execution, right? So I4 must start its execution, right, after I2 or I3 has started its execution and have finished that many number of cycles depending on amount of time it takes before I4 can start. So we formally state this as the start time of J has to be greater than the completion time of its predecessor, or the start time of K is greater than or equal to the completion time of its predecessor, where the completion time is essentially the start time of the node plus its execution time, right? And the objective, of course, is to minimize the make span of the schedule. And what is the make span of the schedule? The make span of the schedule is nothing but the completion time of the entire schedule, which means whichever node which is going to fire last and going to complete, not just fire last, maybe going to complete last, right? Because that is the last node to finish, and that last node that is finishing must finish as early as possible in order for you to have a short execution time. So essentially, the objective of instruction scheduling is to minimize the make span, where the make span is the time for the last node to complete, whichever node which completes last, that completion time of that node, right? That you want to minimize so that your overall execution time is minimized, right? This is the objective of the legal schedule. Of course, the legal schedule has to satisfy all the resource constraints, which is not specified in this particular slide. But oftentimes we always emphasize that all the resource constraints must be satisfied. What does it mean? Supposing, let's say that you have one floating point function unit, then two floating point instructions cannot start at the same time, because they both will compete for the same function unit and only one of them can go in that, right? If the function unit is fully pipelined, then the other instruction can start in the next cycle but not in the same cycle. But if the function unit is not pipelined, then the other instruction can only start after the first instruction has completed its execution. So this information is captured in the form of resource constraint. So whenever you talk about a legal schedule, the legal schedule must satisfy all the dependence constraints which are expressed in this, plus all the resource constraints which are expressed in the form of that, there are enough resources for executing these operations. Okay, now again, this is all talking about the data dependence graph. This is a different kind of a data dependence graph where we have talked about the weights not in the terms of nodes but in the form of edges. So if node 1 takes d1 amount of time to execute, then the arcs from 1 to 2 and 1 to 3 have weights d1, d1. Now in this graph, we will say what is the maximum time that this node this graph would take to complete, right? Of course, if I know that there are these 6 nodes d1, d2, d3, d4, 1, 2, 3, 4, 5, 6, and they take time d1, d2, d3, d4, d5, d6. Sequential execution of them would really mean that it is d1 plus d2 plus d3 plus d4 plus d5 plus d6. That's the maximum time it would take, right? That is assuming that there is no instruction level parallelism, right? Nothing is being used, right? Whereas if I have, let's say, some amount of instruction level parallelism, or let's say I have infinitely many processors to execute, right? Infinitely many functional units to execute, how fast can I execute this graph? No matter how many function units I have, I still have to first complete I1, then I have to complete, let's say, I3, then I have to complete I4, then I have to complete I6. This is one path in my data dependence graph, which says that the execution of 1, 3, 4, and 6 is serial. And irrespective of how many other resources you have, they have to be executed sequentially. Similarly, for that, by the same reason, 1, 2, 4, and 6 have to execute serially. 1, 3, 5, 6 have to execute serially. Correct? They cannot, they cannot be executed in parallel because of the data dependency. So data dependency essentially says even if you have infinitely many resources, this graph will take certain minimum amount of time for completion because of the dependencies that you have. Now you calculate among all the paths which path is going to take the maximum time. And that path is going to tell you the minimum amount of time that would be needed by any machine to execute this particular data dependence graph, right? So that's essentially what is being captured by what is called the critical path. Supposing, let's say in this graph, this is the critical path, right? If that is the critical path, what it means is that the execution time of 1, 3, and 4 together is greater than that of 1, 3, and 5, is greater than that of 1, 2, and 4, is greater than that of 1, 2, right? Because in this path, I take the maximum time, right? That is the critical path, and that is the minimum time any machine can take to execute this graph, because you can't do faster than that. You have to at least spend D1 plus D3 plus D4 plus D6, right? Actually, D6 is missing in all of these equations. My apologies. Let me just mark it. When I was editing it last night, I missed this. So all of this should have D6 also, which is missing. Okay, that's the amount of time it takes to execute, but the critical path is only defined in terms of the edge weights. That's why it is. Okay, that's fine. Now, critical path also tells you something, right? If this is the minimum amount of time it is going to take to execute this graph in any machine, then these nodes 1, 3, 4, and 6, right, they have an importance as opposed to 2 and 5, right? There is some amount of lenience in executing 2 and 5, while executing 1, 3, 4, and 6, there is no lenience, in the sense that whenever an instruction scheduler is trying to schedule nodes, it has to give preference to nodes 3, 4, and 6, or nodes 1, 3, 4, and 6, as compared to other nodes like 2 and 5. So if there is a if there is a resource on which you can either schedule 2 or schedule 3, you would prefer to schedule 3 because 3 is in the critical path. 2 is not, right? So this is an idea that we need to take from this in terms of the critical path. Now, so whenever you are trying to do instruction scheduling, right, instruction scheduling is essentially a list scheduling method where in every cycle you try to schedule one of the many operations, and among the operations you try to schedule one which has a higher priority. And you can define priorities in many ways. One way by which you define priority is in terms of whether a node is in the critical path or not. Because all the nodes which are in a critical path, there is really very little lenience in terms of how much lenience or slack that you have in terms of scheduling them. The nodes in the critical path have a slack of 0, right? So if you schedule them with a slack of 0, you could actually get the best possible schedule, potentially get the best possible schedule, right? Whereas the nodes which are off the critical path, you have some amount of lenience or some amount of slack, and that idea is essentially captured by what is called this earliest start time and the latest start time, right? And I'm not sure whether I would have time to go through this in detail, but let me just give you this example that will actually explain. Okay, so instead of going through the equations, let's just look at this graph, right? Now, in this graph, as you can see, right, this is the critical path. I1, I3, I4 is the critical path, right? So if I have infinitely many resources, even then I would take 4 cycles to complete this graph. And in these 4 cycles, I have to schedule this node in time step 0, this node in time step 1, and this node in time step 3 in order for me to complete it in 4 cycles. If I delay any of these nodes, right, beyond whatever time that I have specified, then I would delay the whole thing, right? So the earliest start time of these nodes is 1. Sorry, this is 0, this is 1, and this would be 3. And of course, the earliest start time of this will also be 1, because if this starts in 0, this can start in 1. The latest start time is the opposite of this, that if this graph has to complete in 4 cycles, then the latest time by which this node has to start is 3. The latest time by which this node has to start is 1, right? Because it will take 2 more cycles, therefore this can start in 3, and therefore this can end in 4. And similarly, this has to start at least in time step 2, so that it will complete in time step 3, and this will complete in time step 4. So this notion is essentially what is being captured in the earliest start time, right, and the latest start time. So the latest start time goes in the reverse way, and you can see these calculations, right? When you have time, you can actually go through the slide and then identify this. The difference between the earliest start time and the latest start time gives you the slack. And the nodes which have the least stack are the ones which are high priority nodes. The nodes which have more slacks have less priority. Now, these are heuristics that you would use in terms of doing your instruction schedules. Okay. Now, so let me just, in general, the instruction scheduling problem is that given that you have a machine with m functional units and a program with n instructions, how do you schedule them across these functional units so that all the dependencies are satisfied and all the resource constraints are satisfied, etc. This problem is NP complete when the number of resources is greater than or equal to 3, right?